So let's say our function was f of x equal to 3x to the fifth plus 2. And I want to find the inverse function. So step 1, write it as y equal to 3x to the fifth plus 2. Step 2, interchange x and y. X equal to 3y to the fifth plus 2. Step 3, solve for y. Step 3 is this 3 where you actually have to do stuff. So x minus 2 equals 3y to the fifth. You can either divide both sides by 3 or multiply both sides by 1/3. So you could say x minus 2 over 3 equals y to the fifth. Or if you prefer, you could write this as 1/3 times x minus 2 equals y to the fifth. Either way would be fine. And then the last step is to take the fifth root of both sides. So y equals the fifth root of 1/3 x minus 2. And then lastly, if you're finding an inverse function, you should write it using the correct notation. So the final answer should be f inverse of x equals the fifth root of 1/3 times x minus 2. And there's your inverse. That's it. You don't have to check. Right? If you follow the process for finding an inverse function, you don't have to show their inverses. The process guarantees it will be an inverse. So there's no need to check that f of f inverse of x is equal to x and f inverse of f of x is equal to x. You do not have to check that if you're finding the inverse. You do have to check that if someone says, show these two things are inverses. Let's do some more examples. Okay, this next, yeah, we'll do that one. So nothing will change on the inside. The inside. By the inside, do you mean like this stuff in here? From step 3? Yeah. Literally step 3 is the only step where you're actually really doing anything. Step 1, write it as y if it's a function. Step 2, change x to y and y to x. Step 3, actually do the work where you're solving for y. And then step 4, literally just rewrite it as f inverse instead of y. But nothing else changes there. You're just giving it the proper name.
Okay, thank you.
Oh, of course. Let's do this next one. Let's find the inverse of. So I'm a fan of this particular type of function because it is a little bit more work. Let's find the inverse for g of x equal to 2x plus 3 over x minus 4. And notice, unlike any of our previous examples, this function has more than one instance of the variable x. Still the same process. So step 1, we're going to write it as y equal to 2x plus 3. You could probably skip step 1 and jump straight to writing as x equal to 2y plus 3 over y minus 4. So y becomes x, and every x becomes a y. So x equals 2y plus 3 over y minus 4. And now we have to solve for y. The difference here between the last ones is there's only one y to isolate, so it was pretty straightforward. Here we have to do a little bit more work. So the first thing I'm going to do is I'm going to multiply both sides by the denominator. So I'm going to say y minus 4 times x is equal to y minus 4 times 2y plus 3 over y minus 4. The point of this is to cancel out the denominator on the right-hand side. Those cancel. So now I've got y minus 4 times x equal to 2y plus 3. Okay, I'm going to write down something wrong. I don't want you to write it down, but I want to show you the wrong way to go here for just a second. So the wrong way to go here would be to subtract 3. And then to divide by 2. Why is this wrong? I solved for y. Well, it's wrong because my solution for y has a y in it. And g of x is a function of x. The inverse, g inverse of x, also has to be a function of x. So your inverse function should only have x's in it. And this doesn't, right? This has y and x. So if your solution for y has some y's in it, it's time to go back to the drawing board. So instead, here's what we're going to do. And this is usually the process for this particular type of problem. We're going to multiply the left-hand side, so distribute the x. X times y is xy, and 4 times x is 4x, equals 2y plus 3. And then we're going to group everything that has a y in it on one side and everything else on the other side. Here are the things that have y's. Yes, that also has an x, no big deal. So I'm going to group all my y things on the left. So I'm going to subtract 2y from both sides. So we're going to subtract 2y. We're going to subtract 2y. So on the left, we're going to get xy minus 2y. On the right-hand side, well, we're going to add 4x to both sides so that these cancel out. So on the right-hand side, we're going to get 3 plus 4x. And now look, all of my y things are on the left, all of my x things are, or all of my, I should say, all of my y things are on the left, all of my not y things are on the right. Now we're going to factor out a y. That's the whole purpose of bringing all the things with y to one side, so we can factor out a y. So factor out a y, I'm left with an x here and a minus 2 here. Equals 3 plus 4x. And then finally, divide both sides by x minus 2. So I end up with y equal to 3 plus 4x over x minus 2. And that is my inverse function. So g inverse of x equals 3 plus 4x over x minus 2. Kind of cool. Something else worth knowing that isn't going to be super important in this class, but I do feel like I should say it. When you find an inverse function, the inverse function have interchanged domains and range, which makes a lot of sense if we think about it, because domain is all the x things, range is all the y things. If we're interchanging x and y, we should be interchanging all the x things and the y things. Notably, the domain here is everything except x equal to 4. Right? X can't be 4. So let me write this down. Let me write this down the other side, just so you guys can see this. Again, I'm probably not going to ask you much about this in general, but it is worth knowing. So if g of x is equal to, I forgot what it was already, 2x plus 3 over x minus 4. And g inverse of x is equal to, what do we got here? 3 plus 4x over x minus 2. Sorry, take a minute there. Or I'm going to write 4x plus 3 over x minus 2. So this function, the domain, is everything except for 4. So I'm just going to write x can't equal 4, even though that's kind of not the most official way of writing the domain. Really, we write like here negative infinity to 4, comma, union 4 to comma infinity. And then the range here, well, let's talk about the range. So this is a rational function. It's 2x plus 3 over x minus 4. It does have a horizontal asymptote. The horizontal asymptote would be y equal to 2 because, right, you've got a degree 1 and a degree 1, and the quotient of the leading coefficients is 2. And not that this is always true, but in this example, this function does not cross its horizontal asymptote. So 2 is out of bounds. And that's actually the only number that's out of bounds. So the range for this function is y can't be 2. I can also show you that because look, if we try and set the function equal to 2, 2x plus 3 over x minus 4 equal to 2, we multiply both sides of x minus 4, you get 2x plus 3 equal to 2 times x minus 4, you get 2x plus 3 equal to 2x minus 8. The 2x is canceled, and then you get 3 equal to negative 8. That's not true. So that means there's no solution, which means this is never equal to 2, which means 2 is not in the range. Okay, let's look over here. Well, for this inverse function, the domain, well, x can't equal 2. And the range, well, again, rational function, degree on top, same as degree on the bottom. Leading coefficient is 4, leading coefficient is 1. So y equals 4 is a horizontal asymptote, and this function will never equal 4. So this function, g of x, the domain is everything except for 4. This function, g inverse, the range is everything except for 4. And vice versa. This function, the domain is everything but 2. This inverse function, the range is everything except for 2. So what I want to point out is that, yeah, sure. The range of a function is equal to the domain of its inverse. And vice versa. The domain of the function is equal to the range of the inverse. Kind of neat. It's actually a pretty useful fact because sometimes we ask about range for things and we can't really graph them very well. This is the way we actually often find the range of a function, is by finding the domain of the inverse function. Kind of cool. All right, let's get back to a couple more practice problems, and then we will move on to talking about the difference quotient, which is totally kind of not related to anything we've done so far today. That's okay. Sometimes you just got to stick two things together because they fit, or because they don't fit. They fit in the class. Okay. How did you find the range? So I found the range by thinking about what the graph looked like. So here, I know this function, if I graph it, has a vertical asymptote of 4. Now let me graph it on the other side because this seems silly to try and graph it here. Sorry. So y equal to 2x plus 3 over x minus 4 has a vertical asymptote x equal to 4. Has a horizontal asymptote at y equal to 2. Has a y-intercept of -3/4, right? If I plug in 0 for x, I get 3 over -4. And has an x-intercept of, let's see, 2x plus 3 equals 0. So x equals -3/2. So in the graph, like if I start here, it's going to go down this way. And then up, it's going to be opposite, so it's going to be up this way. And then to the left, it's going to do this. But I don't cross the horizontal asymptote, right? Like if there's no reason to cross the horizontal asymptote, we usually don't end up crossing the horizontal asymptote, right? If we're not forced to, we typically don't. So there's no horizontal, so we don't ever cross y equal to 2. So that's how we know that y equal to 2 is not in the range. But any other y value is in the range, because you can see that this function, right, gets every value that's above 2 to infinity, every value that's below 2 down to -infinity. That doesn't always work, right? I picked this example very specifically because I knew it worked, but that's kind of the idea. But more importantly, if you can find the inverse of a function, you can find the domain of that and then the range of the original. The horizontal asymptote is y equal to 2. And we're getting that by looking at the rational function, y equal to 2x to the first plus 3 divided by x to the first minus 4. And since the degrees are the same, the horizontal asymptote is y equal to the quotient of the leading coefficients of the top and the bottom, which is 2 on top and 1 on the bottom. That's how we're getting the horizontal asymptote. No problem. Let's do a couple more. I've got maybe 2 or 3 more. So let's do another similar one to the next. So I will definitely ask you one like that on a test for sure. Not like the domain range stuff, just like that type of function where it's a rational function, usually both top and bottom being degree 1. So let's do another one just to practice. Let's say our function was, I don't know, 7x minus 9 over 3x plus 1. How exciting. Excuse me. Process pretty much the same. So you're going to have y equal to 7x minus 9 over 3x plus 1. And then we're going to interchange. X is equal to 7y minus 9 over 3y plus 1. Then we're going to multiply both sides by the denominator. So I'm going to get x times 3y plus 1 equal to 7y minus 9. right? Multiplying the right side by the denominator means the denominator goes away. And then we're going to distribute the x. So I'm going to have 3xy plus x equal to 7y minus 9. You can bring your y's to either side. I'm going to bring them to the left usually, but you can bring them to the right. So I'm going to have 3xy minus 7y equal to, I'm going to bring the x to the left, to the right, so negative x minus 9. Then we factor out a y from the left-hand side, or whichever side the y's are on. So you get y times 3x minus 7 equals negative x minus 9. And then finally we divide by that. So you get y equal to negative x minus 9 divided by 3x minus 7. And lastly, we should say that f inverse of x is negative x minus 9 over 3x minus 7. I'll point out that if you were to do this the other way, meaning if you had decided you were going to bring your y's to the right and your not y's to the left, your answer would be equivalent. It would look a little different. Your answer would look like x plus 9 divided by negative 3x plus 7, or 7 minus 3x. Basically, if you do it the other way, the sign of everything on top and the sign of everything on the bottom is opposite of what it would be. It's still the same though, right? Because if you multiply this by -1 over -1, which is just 1, you get back to that. So either way is fine. Do whatever is most comfortable. Let me erase over here. Okay, 2 more examples and then we'll move on. Yeah, I got time. He says to himself before running out of time. Let's look at this example. Find the inverse of f of x equal to 2 to the x minus 1 plus 3. Okay, so this is an exponential thing. Well, in fact, what am I doing? Let's just follow the steps. Y equal 2 to the x minus 1 plus 3. And then interchange x and y. So x equals 2 to the y minus 1 plus 3. And now I'm going to try and solve for y. So before I can do anything, I need to bring this 3 over. So x minus 3 equals 2 to the y minus 1. And you actually do have a choice here. You could either rewrite it as a logarithmic equation with log base 2. There's definitely one option. You could say, oh, my base is 2. I'm saying 2 to some power is equal to x minus 3. And you could do it that way, and that would be perfectly fine. That's probably the way I would do it. And then we add 1 to both sides, so we get y equal to 1 plus log base 2 of x minus 3. And then we would write it as f inverse. So we'd have f inverse of x equal to 1 plus log base 2 of x minus 3. If I had to say, this would probably be the way I would prefer to do it and the way I prefer you to do it. But you don't have to do it that way. You could also do it this way. So instead of using log base 2, you can say, I'm just going to take the natural log of both sides. Be like, hey, I'm going to do it my way. Natural log of x minus 3 equals the natural log of 2 to the y minus 1. And then we can bring down the y minus 1. So we've got the natural log of x minus 3 equals y minus 1 times the natural log of 2. You could distribute the natural log of 2, but I think it's better just to divide both sides by natural log of 2. So y minus 1 equals the natural log of x minus 3 divided by the natural log of 2. And then finally, y is equal to, if I add 1 plus the natural log of x minus 3 over the natural log of 2. That is also an equally valid answer. It is true that log base 2 of x minus 3 is equal to the natural log of x minus 3, or the natural log of 2. You might recognize that as the change of base formula. Okay. One more example. And this example is meant to kind of aid you somewhat in problem 10 on the homework assignment. I might have to add things to the homework assignment because I just looked at it and I feel like there weren't any questions on the difference quotient. So I'll double check that. If I do add problems to the homework assignment, I will let you all know right away. Either way, I will send you all an email or post an announcement to know that either I did or I did not add something. But I feel like I didn't see any difference quotient problems, so I need to double check on that. All right, last one. Let's say our function f of x is x to the fourth plus 3, and we're given that x is greater than or equal to 0. The reason we're given that is because if it's not, then we don't have a one-to-one function. Right? X to the fourth plus 3 looks kind of like this. And if I just try switching x and y, I get a sideways looking kind of parabola. It's not exactly a parabola. But right, I need the function to be one-to-one, meaning it has to pass the horizontal line test. This function doesn't, but if I restrict x to being greater than 0, then I don't get any of this left side. And now it's perfectly safe. Great, we're happy. So then the process is still the same. Y is x to the fourth plus 3. We switch x and y. We solve for y, so you get x minus 3 equals y to the fourth. And then y is going to equal the fourth root of x minus 3. And that's it. Oh, I should say, and then f inverse of x is the fourth root of x minus 3. That's it. Okay. So let's go ahead and move on to talking about the difference quotient. And yeah. Oh no, there are. Okay, I was just looking. There are 3 problems on the difference quotient. Good. They're all pretty straightforward ones, but we'll do some more challenging examples. So the difference quotient is a name for calculating the slope of a segment connecting 2 points on a function. Let me draw it. I really want to draw it. Yeah, I really want to draw it. So where'd you go? Sorry. Yeah. So let's say we got some function. There's a nice picture in the book, in the notes, which I will somewhat recreate. So let's say our function looks like this. Here's f of x. And there's actually 2 equally valid ways of writing the difference quotient. I'm going to write it both ways to show you. So there's a point, call this point A, point B. So this point here is A comma f of A. I guess I could label it. I might label it. This point here isn't necessarily the highest point, but it might have been the way I graphed it. So this is f of B. And I'm really interested in knowing what the slope of the line connecting those 2 points is. By the way, when there's a straight line that goes through 2 points on the graph, it's typically called a secant line. So I want to know what's the slope of this secant line. And the way we're going to find it, well, we know how to find the slope of a line between 2 points, right? It's going to be the difference in the y's over the difference in the x's. So it's going to be the difference in the y's, so it's going to be f of b minus f of a over the difference in the x's, b minus a. Or if you prefer, right, you can think of this f of b minus f of a as the rise, and b minus a, the run. Right? Slope is rise over run. So that's how we calculate this. Now, this is not the way we are actually going to do it, although it's perfectly fine to do it this way. And you'll definitely see some professors talk about this when they talk about defining the derivative. But usually I prefer by doing this is actually changing things up just a little bit. So instead of writing it like this, I'm going to draw the picture again. So got the same sort of looking function. I can pick, yeah. It doesn't really matter where the point lives exactly. And I'm going to call, instead of calling this point A and this point B, I'm going to call this point x, and this point x plus h. And I'm going to call, obviously, the y value here is f of x. And the y value here is going to be f of x plus h. So if I want to find the slope of the secant line now, sure, close enough, right? So again, it's still going to be the difference in the y's divided by the difference in the x's. So now it's going to be, right, y2 minus y1 over x2 minus x1. It doesn't really matter which order you pick them in, but there is kind of a standard way of doing it. So you could totally have written this as f of a minus f of b over a minus b, but nobody does. This one we typically write as this minus this, so f of x plus h minus f of x divided by x plus h minus x. But the denominator simplifies, right? X plus h minus x is just h. So the difference quotient that I usually prefer to write is f of x plus h minus f of x all divided by h. And that is what is commonly called the difference quotient. I mean, because it literally is, right? We have a difference. Right? In fact, we have a quotient of differences. Right? The top is a difference. Right? We subtract two things. The bottom is a difference. We subtract two things, and it's the quotient of those differences. The difference quotient. I will also mention, right? This distance here is h. And there was one last thing I wanted to say about this. There really was something I actually wanted to say. Oh, I know what it is. Some professors prefer to use delta x instead of h. So some people, and I find delta x annoying personally for a variety of reasons, but some people prefer to write this as, right, you say, oh, look, this is delta x, and this is x plus delta x. So then it's f of x plus delta x minus f of x all over delta x. That's fine if that's how your teacher does it. That's not how I do it. The issue I have with this sometimes you have like delta x's and x's next to each other, and then you can kind of get confused as to what's what. So I would encourage you, I think this is the nicest way to do it personally. It's going to be the easiest to kind of deal with. All right, so we are going to find the difference quotient for various functions. Now, I should have said find and simplify. So the typical instructions for any of these problems are going to be find and simplify the difference quotient for the following functions. So the first function is going to be not too bad. It's going to be f of x equal to, what have I got here? 5x plus 3. Okay. And I want to make you aware of something. So when we are simplifying the difference quotient, well, in fact, let me write it out first before I do. So so I personally like to just start with f of x plus h minus f of x all over h. Our goal every time we do this, our goal is to make that h, the one h that starts off in the denominator. There might be other h's later that end up in the denominator, but we want this h here to cancel out. That is our ultimate goal. And our intermediate goal to get there is that everything in the numerator that doesn't have an h will have to cancel out. Because then once all the remaining things have h's, we can factor out an h and cancel that h with the one in the denominator. So those are our two goals. Cancel out all the not h things in the numerator, and then divide out an h and cancel with the one h in the denominator. You might personally prefer to, so I usually just like jam everything into this formula, but if you find it helpful, you might want to write out what f of x plus h is. So f of x plus h is, well, f of x was 5 times x plus 3. F of stuff is 5 times stuff plus 3, where the stuff is x plus h. So that's what's going to go into my formula here. This is going to equal f of x plus h, which is this, 5 times x plus h minus 3. I don't really need those brackets, but I'm going to kind of try and differentiate between f of x plus h and f of x, which is 5x plus 3. Okay, so now that we've got it right, we're going to distribute somehow, let's see, 5x plus 5h minus 3. And you're always going to have minus f of x. So you're always going to have to distribute the minus sign if it's a kind of function you can distribute to. So it's going to be minus 5x minus 3 divided by h. The 5x and the negative 5x cancel. Oh, it looks like I made a mistake somewhere. I did make a mistake somewhere. So let me actually back up how I know I made a mistake. So I said our goal was to cancel this h out. And I said our intermediate goal was to cancel all the not h things. But look at this. This minus 3, this minus 3, those aren't canceling out. Minus 3 is minus 6. But they should be canceling out, right? I said all the not h things should cancel out. I made a mistake. The mistake I made was I accidentally wrote down, right, f of x plus h was 5 times x plus h plus 3, but I accidentally wrote minus 3 right there. So this should actually be not minus, but plus. And then that should be plus. And then the plus 3 and the minus 3 do cancel out. So if you know things are supposed to cancel, but they're not canceling, don't just make them cancel. Go back and find where we made the error and then say, oh yeah, things work out the right way. But like, if you write minus 3 and minus 3 and just like, oh, they cancel because I want them to, that's going to be a problem. I'm going to have a problem with it. It is, I mean, it's not correct mathematics. So then we've got 5h divided by 5, and then the h cancels. Oh, really, James? Really? 5h divided by 5 and the h cancels? Wow. 5h divided by h, holy smokes. And then the h's cancel and you get 5. A lot of the time, we're still going to have some h's at the end, but in this example, we don't. And here's the reason why. I mean, if you graph this, so if you graph the line y equal to 5x plus 3, it looks something like this. And if you pick a point here and a point here, and you find the slope of the line between those 2 points, well, the line between those 2 points is the same line. And what's the slope of that line? Y equal to 5x plus 3. Anybody? 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 If it was in class, I'd say, show me on your fingers, what's the slope of that line?
What was the question, Jim?
Oh, what's the slope of the line between these 2 points?
5/1.
Right, 5. Slope is 5. Slope is 5. Right, so for a straight line, when you find the difference quotient, you're always just going to end up getting the slope of that straight line. Because, right, you're finding the slope between any 2 points, but any 2 points on the line, the slope between them will be the slope of the line. Okay, that's not typical, but it is true for lines. Yeah, the other thing I want to help you avoid is, so just be careful. I've definitely seen way too many people do this in the past, like they like f of x plus h minus f of x, and they say that f of x plus h is 5x plus 3 plus h minus 5x plus 3 all over h. And then they cancel the 5x plus 3's and h over h becomes 1. That's not the right answer. We know it's 5. So if your answer is 1, it shouldn't be. If your answer is 1, it means you probably made this sort of error. So if you are doing a difference quotient problem and you find yourself getting an answer of 1, you should start over and make sure that you're finding f of x plus h correctly.
Will it be wrong if we always get 1?
Yes. There's only one time when you should get 1. And that's when the function is y equal to x plus a number, a constant. So if your function is not y equal to x plus 3, or y equal to x minus 6, or y equal to x plus a constant, then your answer should not be 1. And none of the examples, I will never give you that problem as an example. So your answer should never be 1. So if you get 1, start over. Let's look at this example. Let's look at, so again, find and simplify the difference quotient for the function. F of x equal to 4x squared plus 5x plus 1. And again, I think it's worthwhile to just write out f of x plus h right at the beginning. So f of x plus h is going to be 4 times stuff squared plus 5 times stuff plus 1. So it's 4 times x plus h squared plus 5 times x plus h. So then the difference quotient, f of x plus h minus f of x divided by h is going to equal all of this. That's my f of x plus h. 4 times x plus h squared plus 5 times x plus h plus 1 minus all of f of x, which is 4x squared plus 5x plus 1 divided by h. Okay, we gotta do a little bit of simplifying here. So you're gonna see x plus h squared a lot. It's gonna be really important that you get it right. So x plus h squared has 3 terms. This is going to equal 4 times x plus h squared is x squared plus 2xh plus h squared. Right? There's an x squared and there's an h squared, but there's also a middle term, which is 2xh. You got to get that middle term. It's viable. And then we're going to have, distribute the 5. We get 5x plus 5h plus 1. And then we're going to distribute the minus sign and get minus 4x squared. Move this h up a little bit so it doesn't feel like it's in the way. Minus 5x minus 1, all divided by h. I can cancel a couple things. I can cancel the 5x and the minus 5x. I can cancel the 1 and the negative 1. I can't cancel the negative 4x squared yet, though, because I haven't distributed this 4. So first I have to distribute the 4. I get 4 times x squared plus 4 times 2xh is 8xh, and then 4 times h squared. And then plus 5h, and then minus 4x squared. All divided by h. Cancel the 4x squared, the negative 4x squared. And then notice, every remaining term on top has an h in it. I'm going to factor one h out. We factor out an h, or divide out an h if you prefer that language. I'm left with an 8x. I'm left with a 4h to the first. I'm left with a 5 divided by h, and then this h and this h can cancel. And our final answer is, I'm going to write it up here so where there's room. Our final answer is 8x plus 4h plus 5. Just like that. Okay, I think I can squeeze in 3 more examples. Let me know if you have any questions about this one. Let's do another one. I'm gonna add one in here. Let's do the find simplified difference quotient for f of x equal to x cubed. So f of x plus h is stuff cubed. Okay, so this is going to be, here's my difference quotient, f of x plus h minus f of x h. X plus h cubed. There is a way to multiply this out. X plus h cubed, you can use Pascal's triangle. I think I've talked about that before. Pascal's triangle, that thing over there. X plus h cubed is going, so we go to the row where the second term is the power that you want. Then x plus h cubed is going to be 1 times x cubed plus 3 times x squared h plus 3 times x times h squared plus 1 times h cubed minus x cubed over h. It's probably worth memorizing what x plus h cubed is. When you take the cube of 2 things added together, it's always like, so for just more generally, right? If you have a plus b cubed, it's going to be a cubed plus 3a squared b plus 3ab squared plus b cubed. So anyway, here, x cubed and negative x cubed cancel out. Everything left has an h in it. So factor out an h. We've got a 3x squared, a 3xh, and an h squared. And then finally, we accomplish our goal of canceling out the h in the denominator. So our final answer is 3x squared plus 3xh plus h squared. That's our final answer. That's our difference quotient simplified as much as possible. All right, I got 2 more examples. I think I can fit them in. These last 2 examples, I will say, I don't think there's any homework problem, at least not for this homework assignment, that is specifically like them. Let me double check now that I've said that. Yeah, there definitely isn't any homework problem that's like them. So all of your difference quotient homework problems are going to be ones where f of x is just a nice polynomial. You just have to multiply it out, cancel stuff, factor out an h. But there are other ones you will see in the future. So I feel like I should do a couple examples just to kind of prepare you for that. So here is an example. What if I want to find the difference quotient for f of x equal to 3 over x? Okay. So my f of x plus h is 3 over not x, but x plus h. So then my difference quotient is going to be f of x plus h minus f of x all over h, which is 3 over x plus h minus 3 over x all over h. And now here's the thing. To subtract these fractions, we have to get the common denominator. So to get the common denominator, I'm going to have to multiply this by x over x and this by x plus h over x plus h. So here's what we're going to do. We're going to, let's see. So we're going to get on top, x times 3 is 3x over, I'm going to leave the x times x plus h not multiplied out. I'm just writing it as x times x plus h minus 3 times x plus h is going to be 3x. I should be careful here. Let's just write it as 3 times x plus h for the moment. Over x times x plus h. And then we have a common denominator, so we put these fractions together. This is going to be x times x plus h is the denominator. And then you've got 3x. And minus 3 times x is minus 3x. And minus 3 times h is minus 3h. So we have to be a little extra careful there. The x is canceled. Great. So now I've got this kind of terrible looking fraction in a fraction. I've got negative 3h over x times x plus h over h. I would love to flip and multiply, right? I've got something divided by a fraction, or so, but I really got is a fraction divided by a fraction. That's h over 1. So I can flip and multiply and say, oh, this is equal to negative 3h over x times x plus h. And instead of dividing by h over 1, we're going to multiply by 1 over h. The h's cancel, and we get negative 3 over x times x plus h. That's our final answer. Right? We still have an h in the denominator. That's okay, because we canceled out the original h in the denominator, which is the one that we cared about.